Problem 1. At time t, a coffee mug has temperature given by this function. Part A. At what rate is the temperature cooling at time t is 0? Answer using appropriate units. A rate is a derivative. Part A asks for derivative at the instant when time is 0. To answer the question, I first compute the derivative at a general time t. After I get the derivative, plug in 0 in t. Derivative of 1 is 0. Derivative of this exponential function is this. How to get the result? By the chain rule. I simplify the function by introducing an intermediate variable u. I let u below negative t over 10. Then the function is simplified to e to u. To find this derivative, I use the chain rule. I insert du to the bottom and du to the top. Then the derivative is equal to this derivative times this derivative. If I cancel du, then this product will go back to this quotient. Derivative of e to u with respect to u is e to u. Now delete u, remove u. Plug in negative t over 10 in u, then I have this equation. Derivative of negative t over 10 is negative 1 over 10. This is the result of this derivative. If you are familiar with the chain rule, you can skip this step, and this step. Directly from here, jump to here. Now, the result of derivative at t is this. Now plug in 0 in t. Then derivative at 0 is negative 7. The units is Fahrenheit per minute. Part B. What eventually happens to the temperature of the coffee as time progresses? Answer using an appropriate units. This part asks for the limit of the temperature as time approaches infinity. To find the limit, I write this function as 1 over e to t over 10. As t approaches infinity, e to t over 10 approaches infinity. So 1 over this guy approaches 0. Therefore, this limit is 70 times 1 plus 0. It is 70. The unit is Fahrenheit. Problem 2. Let function f be this function. Part A. Find all differentiable functions, capital F, satisfying the derivative of capital F is f. There are infinitely many solutions. Part A asks for the most general antiderivative of this function. That is, asks for the indefinite integral of this function. Now I compute this integral. Plug in this function in function f, then I have this equation. apply the summation rule, then I have this equation. To find an antiderivative of this function, e to 3x, I make some tries here. In the first try, I try the function e to x. Derivative of e to x is ex. In the second try, I try the function e to 3x. Derivative of e to 3x by the chain rule is this. 3x derivative is number 3. Now, move the number 3 to the left side, then I have this equation. This equation says that this function is an antiderivative of this function. So this integral is equal to this. X squared antiderivative is 1 over 3 times x to the third. If you take derivative on this guy, then the derivative is x squared. Don't forget to add an arbitrary constant c. Because c is arbitrary, this function is the most general antiderivative of this function. This is the answer to part A. Part B. Among all functions, capital F, satisfied in this equation, determine the solution which also satisfies this condition. In part B, we need to determine the constant c so that this condition is true. Plug in 0 in the x here. Set the result to 0, then I have this equation. From this equation, c is negative 1/3. Therefore, the capital F that satisfies this equation and also satisfies this condition is this function. Problem 3. The limit, this limit, expresses the derivative for some function f and constant a. That is, this limit is equal to the derivative of some function f at some point a. Part A. Determine a function f and a constant a for which the derivative takes the indicated form by definition. The definition of derivative is either this limit formula or this limit formula. These two formulas are from section 3.1. To determine function f and upon a, I compare this equation, the given limit, with this formula. Comparing these two limits, then I can see that a is pi and function f is e to psi of x. Therefore, the answer to part A is this. A is pi. Function f is e to psi of x. Part B. Evaluate the limit by any analytic method you know. In particular, you may simply evaluate the derivative found in part A or use L'Hopital's rule. Don't rely on guesses based on calculator estimates. I evaluate the limit by L'Hopital's rule. Take a review about L'Hopital's rule. The rule says that if this limit is indeterminate by direct substitution. And the type is either 0 over 0 or infinity over infinity. Then we can compute this limit by this limit. The limit of derivative on the top over the derivative on the bottom. Now, direct substitution. I plug in pi in x. By a calculator, I have 0 over 0. So direct substitution cannot determine this limit. Because the indeterminate type is 0 over 0, I can use L'Hopital's rule. By L'Hopital's rule, this limit is equal to this limit. Take derivative on the top over derivative on the bottom. This function e to psi of x derivative is this by the chain rule. 1 derivative is 0. X minus pi derivative is 1 minus 0. Simplify this fraction, then I have this equation. To find this limit, direct substitution. Plug in pi in x, then the limit is this number. This number is -1. Therefore, this limit is -1. Problem 4. Determine the absolute extreme values of the function. The function is a polynomial where x is between 0 and 3. Also determine where these extreme values occur. So sufficient work to justify why your answers give the absolute extreme values. Here is the graph of the polynomial. In this problem, we don't consider the whole graph. We only consider the portion between 0 and 3. That is, we only consider this portion. We need to find the highest and the lowest points of this portion and their locations. From this diagram, we can see that the highest point is here and the lowest point is here. To find the absolute extreme values of this function over this closed interval, we use the closed interval method. Take a review about the closed interval method. To find the extreme values of a continuous function on a closed interval, 3 steps. Step 1, find all the critical points between A and B, or inside this open interval. Suppose we have K critical points. Step 2, compute function values at these critical points and also compute function values at the 2 endpoints of this interval. Step 3, make conclusion. The largest function value here is the absolute maximum function value of the function over this interval. And the smallest function value is the absolute minimum function value of the function over this interval. Now, step 1, find the interior critical points. That is, 5 critical points that are inside the given interval. The given interval is from 0 to 3. Recall that a critical point is a point where derivative is 0 or doesn't exist. So to find critical points, I compute derivative on the function. The derivative is this. Set derivative to 0 and solve this equation. Then I have one critical point. This point is between 0 and 3 inside the given interval. Step 2, evaluate function values at this critical point and also at the left endpoint, the right endpoint of the given interval. The function values are these numbers. Step 3, make conclusion. Of these three function values, the largest is 10. So 10 is the absolute maximum function value over the given interval. The location of this maximum value is x is 0. That is here. This point is the highest point of this portion. Of these three function values, the smallest is negative 38. This is the absolute minimum function value over the given interval. The location of this function value is x is 2. X is 2 is about here. So this point is the lowest point of this portion of the graph. Problem 5. Evaluate each of the following derivatives. Part A. To compute this derivative, I use the chain rule. I simplify the function by introducing a variable u. I let u denote x squared. Then the function becomes tangent of u. To compute this derivative, I use the chain rule. Insert du to the denominator and du to the numerator. Then this derivative is the product of these two derivatives. Derivative of tangent of u with respect to u is secant square u. Now plug in x squared in u. Then I have this equation. Derivative of x squared is 2x. This is the answer to part A. If you are familiar with the chain rule, you can skip this step, and this step, and write your solution from here directly to here. Part B. To compute this derivative, I use this formula. This formula is from part 2 of the fundamental theorem of calculus. This formula says that take integral on function f from a to x. To undo the integral, take derivative. Now, by this formula, this derivative is tangent x squared. Cancel derivative, cancel integral, and plug in x in t. This is the answer to part B. Part C. To compute this derivative, I use this formula again. Please note that in this formula, the lower limit is a constant and the upper limit is just x. In this integral, the lower limit is not a constant. To make the lower limit a constant, I switch the lower limit and the upper limit. Remember, when we switch lower limit and upper limit, don't forget to add a minus sign. Now, the lower limit is a constant, but the upper limit is 3x, not just x. To overcome the difficulty, I let u below 3x. Then I have this equation. But now we still cannot use this formula because this formula requires here is x and here also x. But in this derivative, here is u, here is x, different. To overcome the difficulty, I use the chain rule. I insert du to the denominator and put a du to the numerator and move this dx here. Then this derivative is the product of this derivative and this derivative. For this derivative, now I can apply the formula. Cancel this derivative and integral and plug in u in t. So this derivative is tangent of u squared. Now remove u by plugging 3x in u. Then I have this equation. Derivative of 3 times x with respect to x is 3. This is the answer to part C. Problem 6. A continuous function f is increasing for x greater than or equal to 0. Selected values of this function are listed in the following table, in this table. Using these values, proceed as follows to approximate the integral from 0 to 10 on the function f. Here on the xy plane, I plot the function values in the table. Then I join the points with an increasing and continuous curve. And I suppose this curve is the graph of function f. This integral is the area of the shaded region here. This region is between the graph of function f, x-axis, and between 0 and 10. Part A. Determine the left Riemann sum of function f on the interval from 0 to 10. Using the subdivision of this interval into 5 subintervals of width 2. In this part, the interval 0 to 10 is evenly divided into 5 subintervals. On each subinterval, build a rectangle by using the function value at the left end point of the subinterval as height. Then sum up the areas of the 5 rectangles. The sum is the left Riemann sum in part A. The notation is L5. L means left. 5 means the number of the rectangles. The area of the first rectangle is base delta x. It is 2. Base times height. Height is function value at the left end point of the interval. The second rectangle area is base times height, delta x times function value at 2. The third rectangle area is base times height, delta x times function value at 4, and so on. To compute this sum, I factor out delta x. Then I have this equation. Delta x is 2. Function values at 0, at 2, at 4, at 6, at 8 can be found from the table. Then I have this equation. This number is 76. So roughly, this integral is 76. From this diagram, the sum of the areas of the 5 rectangles clearly is less than the exact area of the shaded region. So 76 is an underestimate of this integral. Part B. Determine the right Riemann sum of function f on the interval from 0 to 10 using the same subdivision as in Part A. In Part B, on each subinterval, we are required to build a rectangle by using the function value at the right endpoint of the subinterval. The sum of the areas of these 5 rectangles is the right Riemann sum in Part B. The notation is arrow 5. Arrow means right. 5 is the number of the rectangles. The area of the first rectangle is base times height. Base is delta x. Height is function value at 2. Second rectangle, its area is base times height. Delta x times function value at 4. The third rectangle, area is base times height. Delta x times function value at 6, and so on. To compute this sum, I factor delta x out. From the table, I can tell these function values. Then I have this equation. This number is 120. 120 is an estimate of the integral from 0 to 10. From this diagram, the sum of the areas of these 5 rectangles is clearly greater than the exact area of the shaded region. Therefore, 120 is an overestimate of the integral from 0 to 10. Part C. Using the information given, can you be certain that the exact value of the integral lies between the 2 estimates given in Part A and Part B? Explain briefly. The answer to Part C is yes. The exact value of the integral from 0 to 10 lies between the 2 estimates in Part A and Part B. The exact value of the integral is the exact area of the shaded region. In Part B, left Riemann sum is less than the exact value of the shaded region. In Part B, right Riemann sum is larger than the exact value of the shaded region. Therefore, the integral lies between the 2 estimates. Problem 7. The graph of a function f, shown on the right, consists of 2 line segments and a semicircle. Using familiar geometric formulas for area, but without explicit formulas for anti-derivatives. This sentence means using integral is let area, this formula. Don't use the fundamental theorem of calculus. Give exact values for each of the following integrals. Problem 7 has A, B, C D, and E, 5 parts. Here I only present my solutions to part A and part B. Part A, find this integral. This integral is integral from -2 to 1. This is the length area of the region between the graph of the function and x-axis and between -2 and 1. The region is this rectangle. This rectangle has no part below x-axis, so area below is 0. Area above is the area of this rectangle. It is base times height. Base from -2 to 1, the length is 3. Height is 2. So the answer to part A is 6. Part B, find this integral from 1 to 5. This integral is the length area of the region under the semicircle, above x-axis and between 1 and 5. This region has no part below x-axis, so area below is 0. Area above the x-axis is the area of this rectangle minus the area of this semicircle. Area of the rectangle is this number. Area of the semicircle is this number. So the answer to part B is 8 minus 2 pi. Problem 8. Evaluate each of the following integrals exactly using any methods you know, including use of anti-derivatives. Here it means you can use the fundamental theorem of calculus. Symmetric means even functions, odd functions, etc. Simplify your answers. This problem has A, B, C, and D 4 parts. Here I present my solutions only to part C and part D. Part C, find this integral. I want to use the fundamental theorem of calculus to find this integral. So I need one anti-derivative of this function. To find an anti-derivative of this function, I make the following tries. The first try, I try the function e to x. Derivative of ex is ex. Then second try, I try e to 2x. Derivative of e to 2x by the chain rule is 2 times e to 2x. Now I move the number 2 to the left side, then I have this equation. This equation says that this function is an anti-derivative of this function. Now, by the fundamental theorem, this integral is equal to this. Plug in the number 3 in x minus plug in 0 in x. Then the integral is this number. Simplify this number, then we have this number. This is the answer to part C. Part D, compute this integral. The function in this integral is a little complicated, and I want to simplify the function. I write the fraction as a sum of these two fractions. The first term in power is x to 1/2. The second term in power is x to -1/2. Then apply the summation rule, I have this equation. To compare these two integrals, I use the fundamental theorem of calculus. Antiderivative of x to 1/2 is this function. Antiderivative of x to negative 1/2 is this function. Now, plug in upper limit in x, lower limit in x, upper limit in x, lower limit in x. Then I have this equation. Simplify this number, then I have this number. This is the answer to part D. Problem 9. At time t hours afternoon, the outdoor temperature is found to be this function. Determine the average temperature for time between 0 and 3, namely between noon and 3 p.m. By formula, the average temperature is this integral. Plug in 48 minus t squared in t. Then I have this equation. Apply the difference rule, I have this equation. Then by fundamental theorem of calculus, I have this equation. Plug in upper limit in t, lower limit in t, upper limit in t, lower limit in t. Then the average temperature is 45 degrees. Problem 10. A projectile is forced along a straight track with acceleration 6 minus t feet per second squared for t greater than or equal to 0, where t is the time in seconds. Assume the projectile starts from rest. That is, initially its velocity is 0. At the origin, initially its position is 0. Part A. Determine the velocity of the projectile in feet per second. Since the derivative of velocity is acceleration, we have velocity is an antiderivative of acceleration. Plug in 6 minus t in A, then I have this equation. 6 minus t antiderivative is this function. Then add an arbitrary constant c. To determine the constant c, I use this initial condition. Initially, velocity is 0. By this condition, c is 0. Therefore, the velocity of the projectile is this function. Part B. Determine the position of the projectile in feet. Since the derivative of position is velocity, position is antiderivative of velocity. Plug in this result in V, then I have this equation. Antiderivative of this function is this function. Then add an arbitrary constant. This time I use d for the constant because I have used c here. To determine the constant d, I use this initial condition. Initially, when time is 0, position is 0. By this condition, d is 0. Therefore, position function is this. Part C. At which time does the projectile reverse direction. When the projectile reaches its highest point, the projectile reverses direction. Because at the highest point, velocity is 0, I set velocity to 0. From part A, velocity is this function, so I set this function to 0 and solve this equation for t, for the time t. Then I get t is 0 or 12. I pick 12. The projectile reverses direction at t is 12. Part D. At which time does the projectile return to the origin? This time I set position to 0. From part B, position is this function, so I set this function to 0 and solve this equation for t. The solution is 0 or 18. I pick 18. The projectile returns to the origin at time is 18. The unit is seconds.